All right, so this next video will be on limits, and we've talked briefly about it, but now we're really going to talk about what does this notation mean, okay? So in Algebra 2, you got comfortable with this type of notation, which it's going to be somewhat incorporated in this, but as you proceed into higher level mathematics, you will start to see this used. Well, you will see it used, all right? So we're going to stray away from what this is, and it's going to be written in a format that's more conducive for courses like calculus, okay? So verbally, what this is saying, and you'll never, unless the question says verbally explain, a limit statement is this, all right? This is the statement. This is the limit notation. But verbally is saying the limit as x, and then the arrow means approaches. And you knew it's the same meaning as in Algebra 2. Approaches c for the function is f of x is. So all of this, the limit as x approaches c is the limit as x approaches c. And that's the notation, okay? The x approaches c goes under the limit, okay? And then f of x is. Okay, and then whatever the output is, that's what it will be evaluated as. Okay, so if we take a look at this piecewise graph, we're going to evaluate the limit as x approaches 1 for g of x, and this entire function is g of x. So we're going to zoom in to x equals 1. So limits, it's not about what's happening at x equals 1, it's about what's happening around x equals 1. So if I look from the left, as we approach, we are approaching the same value as if we were approaching from the right as well, okay? And they both agree. That means at x equals 1, the output is going to be 0. So we can put the limit as x approaches 1 for g of x is 0. Now it says, let's evaluate the limit as x approaches -2 for g of x. So at -2, I can see that we have a removable discontinuity, right? If I were to evaluate, oops, this is g. Let's say g of 2. Hopefully you would say, oh, that's at -2, because we can see at x equals, -2, the output is also -2, okay? But we are evaluating the limit. So limits only care about what is the curve doing as we are approaching this value. So if I look here, as I follow the curve, both sides are approaching the same output. So no, it's not where this is located, but it's going to be here, all right? So again, limits do not care what's happening at x equals -2. They only care about what's happening around it. So as we approach, we are approaching -1. So therefore, this limit will be equal to -1. The limit as x approaches 5 for g of x. So now we're going to go to 5. And if we look at 5, we have a vertical asymptote, okay? So again, yes, we have a vertical asymptote there. What that means is that our functions are going to be approaching infinities. Could be both of them, could be one of them. But if we look at this particular location, from the left side, g of x is approaching -infinity, and from the right side, g of x is approaching +infinity. These are not going in agreeable directions, so that means the limit as x approaches 5 for g of x does not exist. Because the left does not agree with the right. And please don't write equals d and e. That's not an equivalency. You're saying it equals 3 words. Doesn't make sense mathematically, so you can say does not exist. That limit does not exist. So the limit as x approaches 0 for g of x. So we have a corner, or not a corner, I guess it's a cusp maybe. But as we approach it from both sides, we can see that from the left side, it's approaching an output of 2, and the right side is also approaching an output of 2, okay? So that means it will be 2. the limit as x approaches 2 for g of x. So again, I'm going to check what's happening from the left side. From the left side at x equals 2, we are approaching an output that's like, it looks like negative 1.5. Okay? But from the other side, as we approach 2, we're approaching an output of 1. So the left and the right side do not agree as we approach x equals 2. Therefore, it does not exist. And lastly, let's do the limit as x approaches negative 1 for g of x. So at negative 1, if we check both sides, we are approaching negative 3 from the right side and negative 3 from the left side. So therefore, this limit will be equal to negative 3. All right, we'll also be using limits for end behavior. This will be pretty popular. So describe the end behavior of the following polynomials verbally and using limit notation. Okay, so the verbally, it will explicitly say verbally if we expect you to write it out in like a complete sentence. So the left end behavior verbally, we'll call this f of x. We'll call this g of x. Okay, so the left behavior. The left behavior, we can see that it's approaching positive infinity for the y values, but it's going in the negative direction for the x values. So as the x values decrease, because we're going to negative infinity, and to say that it's going to negative infinity, we say decrease without bound. So as the x values decrease without bound, the y values are going to infinity, and we can also say that the y values are increasing without bound. And the left end behavior, the left limit statement. I'm sorry. I was moving too fast. So now we're going to write a limit statement for this. So it says as the x values decrease without bound, so that means the limit as x approaches negative infinity for the function f of x, the y values are increasing without bound. So the y values are approaching infinity. Please do not do this. Like this is not limit notation, okay? The limit is only referring to the x values, okay? When you start to put it under the f of x, is it referring to the x values? Is it also referring to the y values now? It's not correct notation, okay? So please be careful with that. I'll actually leave that there, just so that people remember. And then I'm going to put a big X through it. No, don't do that. Okay. All right, so right behavior verbally. So now we're going to be talking about as the x values are going to infinity. So as the x values increase without bound, the y values, they are going down, so they are decreasing without bound. Sorry, let's just say as the x values decrease without bound, not decreasing without bound. Or increase. Increase without bound. The y values decrease without bound. All right, so to write this statement, now the x values are increasing without bound, so they are approaching infinity. And the function is f of x. And as the x values increase without bound, the y values are approaching negative infinity. So they are decreasing without bound. All right, now let's try g of x. So g of x, the left behavior verbally, so we're going to be looking at this one. So as the x values decrease without bound, the y values are increasing without bound. Again, it's the same with both functions. So I'm going to go ahead and copy this. That's not what I wanted. Okay, let's put that away. I don't remember how to copy on here. Oh well. Leave it there as well, and I'm just going to move it over here, so I'm not wasting your time. Okay, so as the x values decrease without bound, the y values increase without bound. Okay, so same thing for this one. So the statement is actually going to be the same, but one thing does change. We're still approaching negative infinity, but instead of f of x, it is now g of x. All right, these limit statements are function specific, all right? So they all don't work for every single one. You have to tell me what function is this for, all right? And this is approaching infinity again because the y values are increasing without bound. The right behavior, I'm going to go ahead and copy this. Well, not copy, I guess I'm cutting, and I'm moving it over here, and then I'll change it as we need to. So if we look at the graph, as the x values increase without bound, the y values also increase without bound, okay? So I'm going to have to change this to increase. In the other graph, they were decreasing. In this one, they are increasing. So for the limit statement, the limit as x approaches positive infinity for g of x, the y values are approaching positive infinity. Okay. All right, and then lastly for this one is, this is graphically. Now we're looking at them analytically. So write the limit statements. That means we are writing the limit notation, what we did up here, okay? For the end behavior of the following functions. That means we want the right and the left end behavior. Okay, so we have negative 3x raised to the fourth. This is a even polynomial, and it's negative, so that means it's the right side of it is going to approach negative infinity, but because it's even, both sides are going to be doing the same thing. Now, I don't care what's happening in the middle. I only care about what is happening as x approaches negative infinity and as x approaches positive infinity. So for the, actually let's do this. We'll make this a different color. So the limit as x approaches negative infinity, and it's only under the limit that I have that x approaches. For this is f of x, it's going, the y values are decreasing without bound, so they are approaching negative infinity. And then the limit statement for the right is the limit as x approaches infinity for f of x is also approaching negative infinity because the y values are decreasing without bound. All right, the next one, we have 5x cubed plus 2x squared minus 7. It's an odd function, which means the tail ends will disagree. They're going to go in opposite directions. And the leading coefficient is positive. So we have 5 going up. Sorry, not 5 going up. We have it increasing and decreasing. Again, I don't care what's happening in the middle. I only care about the end behavior. So x values decreasing without bound, and then x values increasing without bound. So for the left limit statement, which means the limit as x approaches negative infinity, for g of x, it's not f of x anymore, my y values are decreasing without bound, so they are approaching negative infinity. And my right limit statement, which means x is approaching positive infinity for g of x, my y values are increasing without bound, so now we are approaching positive infinity. So how you wrote it in Algebra 2, it's in there, because g of x is technically y, but now we can see how it fits into the picture of limit notation. And And C, this is a rational function, which is the next unit. So this is kind of an introduction. But you have a calculator. If you plug this into the calculator, you can see that you have an EBA at 2. Your end behavior asymptote at y equals 2. And I know this because if we look at this and think back to when we did division, you can take 2x divided by x, which is equal to 2, and that's going to be your quotient, okay? So that means we have an end behavior asymptote at y equals 2. We'll do more of this in rationals. Don't stress about this if you don't remember it. But let's see. So we don't exactly know what this function is doing, but we do know that it's going to be approaching the end behavior asymptote. Whether it's above or below, it doesn't matter because it's always approaching the same value. All right, so as x, so the limit as x approaches negative infinity for g of x again, they are approaching the end behavior asymptote. Oops, this is an actual value, so we can just say equals 2. And then the limit as x approaches positive infinity, so the end behavior going to the right for g of x is also going to be approaching 2. So your EBA is going to tell you where are your limits going to be approaching. And the last one, for h of x, we have negative 10 over x squared. If you think back to your parent functions, this is x squared. So again, there is a vertical asymptote, but we don't really care about that. And we know that for this one, it's going to be reflected. So we have both curves down here. But for this one, the EBA is going to be y equals 0. So that's what we will use for this one. So as the x values decrease without bound, we have the limit as x approaches negative infinity. The function is h of x, and this is approaching 0, okay? And then as the x values increase without bound, so going to positive infinity, for h of x, it's also approaching 0, okay? So again, that EBA will tell you where your end behavior is approaching for your limits. Cool? All right, that's the extent of the limits for this unit. We will see them more in the next unit, and then the next video will be on regression. Hope this helps.